Hi, everybody.
I'm Charina.
Hi, everybody. My name's Erik. And today, we're going to have a dialogue with all of you about quantum computing in 3 acts. Act 1, facts. 2, fiction. And 3, the future. Now, we have plenty of time for questions, so please feel free to ask us anything. Charina and myself, we're here today presenting on behalf of a merry band of our team members here, the quantum mechanics at Google Quantum AI. Woo-hoo!
Act 1, facts.
Whether you know it or not, you're surrounded by quantum mechanics. Take, for example, how light interacts with matter, fluorescence to photosynthesis, and the photoelectric effect. Even how plants turn sunlight into food, or how birds use the Earth's magnetic field to migrate. Quantum mechanics gives rise to amazing and beautiful things in nature. Nature is quantum mechanical. Objects that follow the laws of quantum mechanics have interesting properties. Consider superposition, where objects can be in many places at the same time. And entanglement, this lovely property of sharing quantum information in a way such that you can't separate the system. Quantum is the language of nature, and I believe that art inspires our creativity, it propels us to explore scientific possibilities, and it welcomes folks to ask questions. And in our lab, we celebrate the places that we hope to protect with a quantum computer by covering them in art. So that image there I just showed you is something we wrap around our quantum computers, hugging it like the Bob Ross blanket of love. And I can contest, this isn't your typical science lab. It's an art and nature-inspired lab for humans and the future of computing.
So why? Why build a quantum computer? You know, Erik said nature is quantum mechanical. The Nobel Prize winner Richard Feynman puts it this way: nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. Look, even with today's best AI, it is difficult, even impossible, to calculate many things in nature exactly. And that would be a very, very useful application, many useful applications. I'll share one that's personally motivating for me. 20 years ago, my husband, then friend, was facing a very tough cancer diagnosis. He went through multiple rounds of chemo, radiation, nothing was working. Ultimately, thankfully, due to an experimental treatment, he was cured. Fast forward to today, he's an oncologist, he's a cancer researcher, he's helping to treat other patients, right? And not everyone is so lucky. Thank you.
Yeah.
Yeah, he's amazing. But you know, not everyone is so lucky. There are many untreatable cancers. There are many other diseases. There are many other conditions. If we as a society had the opportunity to better understand nature, we could use that to increase our chances of solving many of these problems, helping more people. And that's where quantum computers come in. So our thesis is here. Quantum computers will be a powerful tool. Just talked about quantum simulation, the idea of the use of a quantum computer to simulate molecules, materials. Now, this is expected to have what's called an exponential speedup. That is, calculation performed on a quantum computer will be exponentially faster than that performed on a classical computer. This is one example. Quantum machine learning. Here's another example application. So this is the use of a quantum computer to learn from quantum data. The quantum data is things like electronic data, magnetic data, data from quantum sensors. Now, it is expected to also have an exponential speedup. Another way to think about this is that a quantum computer can learn from exponentially less quantum data than it would take for a classical computer. You can imagine lots of reasons why this could be important. Now, there's an open question, and it's a good question, whether or not quantum computers will have a speed up for learning from classical data, things like images, video, text. That's being explored right now. It's a good question, but remains to be seen. There's other applications for quantum computers too, and this is really what drives us. Our mission at Google Quantum AI is to build best-in-class quantum computing for otherwise impossible problems.
Woo. All right, speaking of impossible problems, maybe even just difficult problems, maybe I could get a show of hands of the last time that you reached for an abacus to solve a problem. Right. In a room full of developers, I think we all have a practical practice, a good practice of reaching for the right tool at the right time. All right, traditionally, classical computers have been such tools. They're widely valuable and they're widely variable. Maybe if we just make the abacus fit in our pockets, we take them around with us more often. However, classical computers are in the same computing class as an abacus, as they are governed by Boolean logic. And we just talked about quantum computers are governed by quantum mechanics. In each of these styles of computing, there are the fundamental building blocks. In classical computing, you have bits, either 0 or 1. In quantum computing, you have quantum bits, or qubits, which can be in a superposition state of 0 and 1 at the same time. Now we have logic in these systems, right? So for a classical system, you can think of this input here of the NOT gate, which just takes the input and inverts that from 0 to 1. And in quantum computing, we have this lovely gate that doesn't even exist in classical computing, the square root of NOT, which can take 0 and prepare the superposition state of 0 plus 1. And qubits are real physical things. They exist in the real world. All right? You can take any two-level quantum mechanical system. All right? You could take what Mother Nature provides, say the electron, spin up or spin down, and that could be encoded as 0 and 1. You could find some particular atom that only has an excitation states that are just ground and say excited state. And at Google, we actually fabricate artificial atoms with just 2 levels. And we do this by making them out of superconducting electrical circuits. We make them just like you would, like, say, a computer chip, with the difference that we have to cool these down, so we need refrigerators to actually make these systems cold. So you can think of these artificial atoms as resonators. We've got an image of them, one of those in the far left there. Inside of that, the X there is the capacitor. And as I've zoomed in on this with a scanning electron microscope, you can see this loop of metal around there forms an inductor. So together, this capacitor and inductor create a resonator. And to go from these qubits all the way up to a quantum computer, you need some additional 10,000 components in a sense to support that quantum processor so that we can cool it down and communicate with it. If we could roll the video. Once we take that processor, we actually mount it in a package, and we put it at the bottom of our refrigerator, and you can see a bunch of radiation shields that go on to basically shield the higher temperature stages from those lower ones to keep that cold. We put on a vacuum can, we basically evacuate the space, so it's basically empty of space, and we have a mu metal shield that wraps around it to protect it from the Earth's magnetic field, and then we wrap it in the Bob Ross blanket of love. We push a button, we walk away, and a few days later, the system is cold. So now that we've created this cold, quiet, and Zen-like space for our qubits, we can set out to communicate with them. So let's continue with this idea of resonators and maybe even this music metaphor. We'll lean into that a little bit more. So in music, you have notes created by instruments that create these sound waves. In quantum computing, you have quantum gates that are created by, in this case, our control system you can think of as synthesizers. So if we were a band, we'd have a whole bunch of synthesizers on stage to make these arbitrary waveforms that shape these electrical waves. And when these pulses are on resonance with the qubits, they perform operations. They dance. They're entangled. So programming a sequence of gates is like composing music or writing a song. These compositions are the algorithms that perform calculations. Okay? So what are some of the compositions that we've made today? Well, we've created some intriguing states of matter, some of which that have yielded many dozens of Nature and Science articles. And you can think of these as maybe like our albums, if you like, or glimpses into the secrets of nature. So we've made time crystals, which is a great name for a band, or a piece of jewelry maybe. Who doesn't want to wear a time crystal bracelet? Time crystals have an astonishing physical property. And they change their state periodically in time without exchanging any energy with the environment. All right, this is about the closest we can come to a perpetual mobile machine without violating the laws of physics. Also on our Sycamore quantum computer, we created novel states of matter that emerge when one mixes quantum operations and measurement. So it's a bit like a quantum take on Zeno's paradox. So this is the classical paradox that it contemplates if you continue to make a measurement on something, motion stops. In quantum mechanics, measurement is very important. It's actually what takes the superposition state and collapses it to a definite state. In this experiment, we mixed the dynamics of measurement and entanglement across 70 qubits and found just the right balance to show this really large, complicated many-body quantum system. Another example that explores the memory and identity of particles in space and time is this experiment. This is really cool. We demonstrated in this case for a system, A plus B does not equal B plus A. So you can think of a house made of Lego bricks and picture that someone is just swapping two identical yellow bricks. From the outside looking in, it doesn't look like anything has changed. But quantum physicists had actually predicted that for particular systems, if you change the identical properties, these identical particles, the overall properties of the system changes. So this was demonstrated for the first time on our quantum computer. And it's a lovely reveal of the long anticipated type of matter and has applications in quantum error correction.
Act 2, fiction. Now this act is important as well because there is a lot of fiction out there about quantum computers. Myth number 1, quantum computers are already better than supercomputers. Fact check. To date, no quantum computer has outperformed a supercomputer on a real-world application. Now, here's a picture to help you think about this. Imagine a 2D graph. On the x-axis, you've got usefulness. The y-axis, you've got difficulty. And you can see along that y-axis, right, different gradations. So at the bottom, something like beyond brute force would take you days on your laptop or your desktop. Classically expensive, taking months on a supercomputer. Or classically intractable, taking years or more on a supercomputer. Now, the 3 examples Erik just talked about, they're really cool explorations of science, new discovery. They exist in this bottom left-hand quadrant. There's also examples on either end of the axes. So on the far right, a quantum computer plus quantum Monte Carlo chemical simulation. Of course, that's extremely useful to be able to do that. To date, that has not been proved to be beyond brute force in terms of difficulty. On the extreme end of the other axis, you've got an algorithm called random circuit sampling. Now, again, to date, this is the only algorithm that has proved to be beyond classical, classically intractable on an actual experimental quantum computer hardware. Now, Google first demonstrated this algorithm in the experiment on our own hardware in 2019. Since then, right, classical computing has gotten better, so has quantum computing. And in fact, we've continued to increase that gap by many orders of magnitude, which is great. It's been a very, very helpful benchmark problem. However, you note that random circuit sampling is all the way to the left on the x-axis. Currently there are no known real-world applications of random circuit sampling. You can look at lots of other types of experiments that have been run on quantum computers to date. Lots of really important work being done, but all of them exist in one of these 3 quadrants. To date, there have been no experimental demonstrations in that upper right-hand quadrant, what we call quantum benefit. We and many others in the field are working very hard towards getting new experiments into that quadrant. And we expect, over the next few years to start to see more, especially as people push algorithmic development and, importantly, the hardware performance. Okay, myth number 2. Quantum computers will replace your computer. We hear this a lot too. Fact check. Quantum computers will be complementary to classical computers, outperforming them for some, but not all, classes of problems. Again, let's use this graph as a way to think about it. The myth is here in the purplish pink, right? We hear this a lot. Quantum computers are just going to be faster than classical computers at every single application. That's the myth. We know if you think of just the set of commercially relevant applications, classical computers are still going to be better. They're going to be the better choice for some types of problems. And of course, as we continue to push the hardware, quantum computers will be better for other classes of these important problems. So when you see a claim like this, there's a couple of factors that you can think about to really evaluate the claims for yourself. The first, comparison to classical computing. Where does this claim actually exist along the y-axis? Real-world application. Where does this claim actually exist along the x-axis? And then, of course, expert validation. Are other experts in the field, are others really supporting this finding? Myth number 3, the more qubits, the better.
This is my favorite myth.
Yeah, you hear this a lot, right? It's like we'll hear claims like, oh, we've got 100 qubits, 1,000 qubits, 10,000 qubits. The more, the better. And of course, the fact check, like with anything, quality, not just quantity, is important. So a way to think about this is to consider a measure called the gate error rate. So you can see plotted here, you've got 10 to the minus 2 at the top. That is making one error in every 100 gates. This goes all the way down to 10 to the minus 12 on the axis, so making one error in every 10 to the 12 gates. And of course, as you go down in error, that's better. Now, if you look at where physical qubits are today, they are in this regime of 10 to the minus 2 to 10 to the minus 4, right? And this is good. It's taken lots of hard work and dedication to get here. You also notice a spread, right? Some of the best physical qubits are a couple orders of magnitude better than okay or kind of lower performing qubits. So that, that's great, but it's nowhere near where we need to be. None of the physical qubits that we have today are close to where we need to get to for real world practical applications. We're going to need something called quantum error correction to get there. And again, when you think about claims, here are things that you can think about to really evaluate them and get the full picture of what's happening on chip performance. The first is, of course, physical qubit count. That matters. You do need to have more qubits for harder computations. Second, physical qubit quality. What does that look like in terms of the physical qubit performance? Speed, how fast are these computations actually able to happen? Qubit connectivity, that gets to a measure of the types of circuits you're able to run on your chip. And then finally, error rate, right? Overall logical error rate, what kinds of applications are actually possible with this claim? Act 3, the future.
Thank you. So what is it going to take to build a useful quantum computer? Well, we're going to need all the things that Charina just mentioned, and I'll summarize those as quality and quantity, which I've plotted here on the x-axis. And we've kind of labeled some meaningful milestones along the way. In 2019, we created the first classically intractable benchmark. All right, this shows up on the top left part of what Charina just showed a moment ago in her plot. Some folks called this the Kitty Hawk moment for quantum computing. We'll call it here milestone 1. It's architecture agnostic, so any quantum architecture can participate. This benchmark basically is, I would say, table stakes if you want to have a seat at the table to building a useful quantum computer. Okay? In it, one shows that their quantum processor, their quantum computer, can perform a specific calculation that no classical computer can perform. All right, and if we want to squash all of the distractions that our qubits face as we scale up, we're going to need quantum error correction. That was what Charina just showed you. In 2023, just last year, we were the first and only team to show that as we made our system bigger, the errors did not increase. The overall system performance actually got better. All right? The logical error rate actually improved. So this is kind of a big deal. So let's just dwell on this for a moment. We call this milestone 2. So if you consider a surface area with some amount of errors, and you actually increase that cross-section, right? The errors are actually, you would think, are going to scale with the area. All right? And what we showed with kind of against that intuition, with great physical qubits and really exquisite control, that we were actually able to reduce the error and the system actually got better. All right? So the first time ever we showed that quantum error correction works. Milestone 3. All right, this can be thought of as our transistor moment in quantum computing. We estimate that we're going to need about 1,000 physical qubits with exquisite control, and these qubits will be checking in on their nearest neighbor. This is something that Charina mentioned a little bit about how we have connectivity. These are nearest neighbor couplings, and basically they're talking to each other, making sure everybody's okay. It's kind of a form of how quantum error correction works. We basically have that system set up, we can run this error correction code and basically keep this logical qubit alive until we turn the power off. Okay, and so to summarize, if classical computers can do what your quantum computer can do, there's really no point in doing it, right? That's milestone 1. And if errors get worse as you add qubits, you can't scale up. That's milestones 2 through 6.
So we expect that the majority of useful applications are going to become possible with a milestone 6 or better computer. Importantly, though, early processors can be used along the way, right? We're already starting to use them. And you'll notice here, right, these are arrows going to the right. We don't expect to stop at milestone 6. We expect that we and the field will continue to push performance beyond to really start to access more capability. And again, why are we doing all of this? Here are some of the future applications that we expect. Drug discovery, I mentioned earlier, fusion energy, fertilizer production, quantum machine learning. These are some of the applications that we think will become possible. And we think there's probably going to be others too.
No, we'll see. I think this is a big part of what our team has been thinking about is, look, we are a small team and we want to actually bring everybody in the world to participate. So just like the inventors of the first computer, the ENIAC, built in 1945, could not have imagined all the ways that you developers are using computers today, right? We believe and we hope the same is true for quantum computing. This is why our team, the Google Quantum AI team, partnered with the X Prize and Google.org to sponsor an X Prize for real-world impact on quantum computers. It's a $5 million prize. It's open for submissions now, and it's focused on how quantum computing can be leveraged to solve the challenges of really all these impossible problems that we may have, right? So we believe in achieving the impossible, and we believe this prize will help mobilize these great ideas and turn those impossibilities into reality. So we're not the only ones working on this. I think a new workforce is needed to make this future possible. It's going to take an error-corrected quantum computer, a worldwide network of people, brains, perspectives, ingenuity, developers, just like you and your neighbors sitting around you, to help build this future. So please consider yourself invited. Maybe you can see yourself in some of these photos already. You can show up as a scientist, a software engineer, a technician, an artist, a teacher, an enthusiast, a developer, to come be a quantum mechanic. So let's grow this community and help build the tools that will help prolong our existence here on Earth. Thank you.
We'd like to leave you with this last point, again, bookending the presentation with another quote from Richard Feynman. He says, "By golly, it's a wonderful problem because it doesn't look so easy." It's not easy. It's really, really challenging. In fact, sometimes it's frustrating, but it's really fun. It's rewarding. We're excited by the opportunities. We feel really lucky to get to work on this. If you're interested to learn more, check out our website. Come visit us at the AI Sandbox. And we're just really happy to be here. Thank you.
Thank you all.